Welcome to this lecture number 32 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic that we are currently discussing is fluid flow at very high Reynolds numbers. As I mentioned in the last lecture, the solution of the differential balances, namely the Navi-Stokes equations, are extremely difficult when you consider the Navi-Stokes equations in their entire form. So often it is necessary to make simplifications of the Navi-Stokes equations in appropriate flow regimes. Many practical applications in chemical engineering and in other engineering contexts happen at very high Reynolds numbers. The fluid flow at such applications in such applications happen at very high Reynolds numbers. So it often pays it's often beneficial to look at what is going to happen to fluid flows at very high Reynolds numbers. In order to do that, we first looked at the non-dimensional Navi-Stokes equations, which look like this. Plus V star dot del star V star. All the start quantities are non-dimensional. This minus del star V star plus 1 over Reynolds number times del star squared V star plus the non-dimensional gravity term, which is let us just ignore gravity for the moment. Okay. And so this is the non-dimensional form of Navi-Stokes equation, and we know that the Reynolds number is a ratio of inertial to viscous forces. It is a measure of inertial forces in the system to viscous forces in the system. And when the Reynolds number is very large compared to 1, this implies that viscous forces are small compared to other forces in the system. So, as a first approximation, we can think of neglecting the term multiplied by 1 over Reynolds number, because 1 over Reynolds number is very small, and assuming that this quantity, that del star squared V star, is a reasonably well behaved quantity in the sense that it is a non-dimensional quantity. So, it should not be very large, then we can neglect this term. There are issues with this neglect, and this forms a very important part of discussion in fluid mechanics, and I will come to that a little later after 1 or 2 lectures. But right now, this is the most sensible thing that appears, this is the most reasonable thing that appears plausible at this time. So, we will go ahead with this assumption, and the resultant equation is called the Euler equation, where you have thrown away the viscous term. So, we will have simply this is the dimensional form of Euler equation, and if there is gravity, you can put rho times c. This is the dimensional form of Euler equation. Okay. Now, once you had the Euler equation, the last lecture we proceeded further, and then what we did was to rewrite this term V dot del V term as del of half V dot V plus del cross V cross V, and del cross V was omega. So, this became omega cross V. So, once you substitute this entire thing back in the Euler equation, and if you dot the entire equation with with an elemental displacement dr, we obtained plus 1 over rho del p minus g dot dr is 0. Notice that omega is called the vorticity in fluid mechanics. It is a measure of fluid rotation about a given point in the flow. Okay. If there is vorticity, that means that about a point in the flow, the neighboring points undergo a circular motion about a given point. So, there is this does not correspond to bulk rigid body like motion of the entire rotation of the entire fluid volume, but about a given point there is a differential about a given point. If you consider differential displacement vector, the neighboring points are moving in a circular motion about this point. So, that is the meaning of vorticity, non-zero vorticity. If the vorticity is 0 at each and every point in the fluid, then such flows are called irrotational flows. Okay? We will come to that a little later. Right now, from basics of partial derivatives, if you have del phi dot dr, that will give you the change in the value of the function phi between the 2 points. Suppose you consider 2 points which are connected by an elemental vector dr. If you take the gradient at this point and dot it with dr, this will give you for small dr the change amount of change the function is going to incur when you march a tiny distance dr. So, if I dot this with dr, I will get the first term will remain as such. Okay. The second term will become d of half v dot v. The third term will become dp by rho. Okay. If you look at, there are 4 terms, okay, 1, 2, 3, there are 5 terms. So, okay, for the moment we are going to restrict ourselves to cases where omega cross v dot dr is identically 0, only then the equation can be simplified. I pointed out in the last lecture that this can happen if either omega itself is 0, that is the flow is rotational, or the flow is along a streamline, or if you consider dr or dr along a streamline, that is if you are marching along a streamline, then that is true. Okay. So, under these circumstances, either when the flow is rotational or when you are considering along a streamline, this term is identically not there, this term is not there. Okay. So, we are left with just dp by rho plus you had g dot dr, okay, is 0. Now, let us arbitrarily write g as minus g times k, it is pointing in the minus z direction, and dr is nothing but dx times I plus dy times j plus dz times k. So, if I dot these two, I will get g dot dr as, I am sorry, there is a minus sign here if I remember correctly, there is a minus g here. So, the minus should happen here. Okay. So, g dot dr will just become minus g dz. Okay. So, this is g dot dr is equal to minus g dz. If I substitute this back in here, the two negatives will cancel to give you dv dt dot dr plus d of v dot v plus dp by rho plus g dz is 0. Okay. Now, if I integrate, if I consider that dr is along a streamline, there are only 2 cases we can consider, that is dr is along a streamline or the vorticity omega is identically 0. So, if dr is along a streamline and I integrate the above equation between points 1 and 2 along the same streamline, points 1 and 2 along the same streamline along a given streamline. Now, then further make the assumption that the flow is steady and incompressible. If I make these 2 assumptions, okay, then if the flow is steady, then this term goes away. If the flow is incompressible, rho is a constant. Okay. Then if I integrate along any 2 points, I will get integral from point 1 to point 2 dp by 1 over rho dp plus from point 1 to point 2 d of v dot v is v squared and there is a half and then plus g dz. is 0. This implies that P2 by rho plus half V2 squared plus G Z2 minus P1 by rho plus half V1 squared plus G Z1 is 0. But since points 1 and 2 are any 2 points along a streamline, this implies essentially that P by rho plus half V squared plus G Z is constant along a streamline. In an inviscid flow, steady, inviscid, steady, incompressible flow. These are the assumptions we made to derive this. So, it is good to keep them in mind, because it is always important to know when such equations are applicable. So, what we have shown essentially is that this is the Bernoulli equation. So, strictly speaking, the Bernoulli equation is valid for an inviscid flow, steady. The Bernoulli equation written in this form, that is P by rho plus half V squared plus G Z being a constant along a streamline, it is valid for a steady incompressible inviscid flow. Now, we also had this other assumption. So, the first assumption, well, we considered this first, dr along a streamline. We also had this as another possibility that omega is identically 0. So, let us go to this equation and integrate this now, considering the other assumption that omega is identically 0. So, we will go back. So, we will go back to this equation and consider the assumption that instead of considering along a streamline, we will consider omega is identically 0. Okay. So, we are going to take this equation. So, we again have d of half V squared, V dot V is V squared, it is the square of the magnitude of the velocity vector, plus dP by rho plus G dz is 0, considering that vorticity is 0 everywhere in the flow. Even with this assumption, this equation is valid. This equation is valid for two different types of assumptions. One is that the flow is the differential vector dr is considered along a streamline, then that term omega cross V dot dr is 0. Or if you identically consider, this is a much stronger assumption. This is a much more stronger assumption, because you are assuming that the flow is irrotational everywhere, but it also leads to lots of simplifications. This, although it is a very strong assumption, it leads to a lot of simplifications. So, if you assume that, you will again get the same equation, but now you can integrate between any 2 points in the flow, because you can dot it with dr. Now, dot with dr, and there is no necessity that dr is along a streamline, and dr is an arbitrary vector displacement. Can integrate between any 2 points in the flow. Okay. Then again you will get the same equation, P by rho plus half V squared plus G Z is constant anywhere in a flow provided the flow is inviscid, irrotational, steady, and incompressible. Okay. So, these are four, this is the same equation, the same type of equation results, but the types of assumptions that we make to get this equation, that P by rho plus half V squared plus G Z is constant being constant anywhere in the flow, there are completely different types of assumptions. Basically, you need not consider dr along a streamline, it can be any 2 points in the flow, but we are making a much stronger assumption that the flow is irrotational. So, now we have to really worry about the following thing, that when can a flow be considered irrotational, because we are going to tell shortly, we are going to see very shortly that when the flow is irrotational, it leads to lots of simplifications in finding the velocity fields at higher Reynolds numbers. So, when we can ask the question when the flow is likely to be irrotational, okay, the answer turns out to be that suppose you consider a body shape like this. Okay. This is called an airfoil. This is a solid body. Essentially, it is a body that looks like this. Okay. And since it is a long, this is very long, the width of the body is very large compared to other dimensions. The other dimensions are thin. So, I am going to just draw a cross section of this. I am going to take a cut across a plane, and it is going to look like this. Okay. So, this is called an airfoil. Essentially, this is like a cross section of an airplane wing. It is a model of a cross section of an airplane wing. Okay. So, if you consider flow past an airfoil, far away the flow is uniform. Okay. You have a uniform flow. Okay. If you have a uniform flow, one can immediately find out that the flow is irrotational also. Uniform flow has no vorticity. It is a kinematic feature of an uniform flow. If you have a uniform flow, regardless of whether you consider the fluid to be viscous or the ideal fluid, inviscid fluid, if you merely compute the vorticity, since there are no gradients in the flow, the vorticity has to be identically 0. Okay. So, vorticity is 0. Okay. So, there is no vorticity when the fluid is flowing far away from the airfoil. The moment it reaches close to the airfoil, what is going to happen is that in reality on the surface of the airfoil there is the no slip condition. Let us assume the airfoil is stationary, the fluid is moving. So, on the surface of the airfoil, at each and every point on the surface of the airfoil, there is a no slip condition which forces the fluid to retard to 0 velocity, that is, it forces the fluid to reach 0 velocity. Now, little away from the surface of the airfoil, the fluid has to move, okay, because you are considering a steady flow, fluid has to move past the airfoil. So, there will be a region where the velocity goes from this uniform value to 0 on the surface of airfoil. Now, that region, it turns out that region is very thin, at least for objects like an airfoil. So, again the flow is uniform here, okay, roughly uniform here. So, we can imagine that the vorticity in the flow is 0 here, but here within this zone close to the surface of the airfoil, there are velocity gradients, and it is not immediately clear whether the vorticity is 0. Vorticity is the curl of the velocity vector, and curl has gradients in it. So, whenever you have gradients of velocity, it is likely that there will be non-zero vorticity. So, the assumption that the flow is irrotational is well valid when you consider regions away from the solid surface, but on regions close to solid surface the vorticity is not 0. So, the irrotational flow assumption will break down in regions close to solid surface. In some sense, the solid surface, we can think of or imagine the solid surface to be a source of vorticity, because by forcing the fluid to reach 0 velocity on its surface, it is creating or setting up velocity gradients and high regions of shear, and such that is those are the regions where the vorticity can be large. So, you can imagine that vorticity is generated in the solid surface and it is swept away by the flow far away. So, there has to be a zone where vorticity is confined, okay, and that zone is actually called the boundary layer. I will come to that a little later. So, essentially when you are away from the solid surface, it makes sense to assume the flow to be irrotational, and generally the flow Reynolds numbers are high such that you can ignore the viscous terms. So, the flow is anyway inviscid approximately speaking, far away from the solid surface, and in addition it is also irrotational. So, the moment you make the inviscid assumption, you get the Euler equation. The moment you make the irrotational assumption, that is the vorticity is 0, then you get the result, the Bernoulli equation, that p by rho plus half v squared plus g z is constant across any 2 points in the flow. You need not follow a streamline. Such inviscid and irrotational flows are called potential flows. Okay. Now, the reason why they are called potential flows is not far to seek, because when you assume the vorticity is 0, this is an irrotational flow. This is a kinematic constraint, that is, you are simply assuming that there is no rotation about a point in a fluid and at each and every point in the fluid. This is a purely kinematic condition. This has nothing to do with whether viscous forces are dominant or inertial forces are dominant, but it so happens that this assumption is more and more applicable at higher Reynolds numbers, because if you consider like the example I suggested, when you have flow past solid surfaces, a little away from solid surfaces the fluid flow is uniform, and so we can expect that the vorticity is 0 or negligible there, and all the vorticity is confined close to the solid surface in a region called the boundary layer. So, even though this assumption is a purely kinematic assumption, it has by itself we cannot say whether this is a good assumption for viscous flows or inviscid flows, but by looking at the nature of why vorticity is generated and the nature of flows at higher Reynolds numbers, we can say that this assumption is more and more valid at higher and higher Reynolds numbers, especially in fluid flow past solid surfaces, because the vorticity is generally 0 in regions away from solid surface, okay, or small. So, it makes sense for us to assume that the vorticity is 0, that is negligible. So, these are irrotational flows. Whenever you have curl, vorticity is curl of the velocity vector. Whenever you have curl of a vector field is 0, you can write the vector field to be the gradient of a scalar function, okay, and conventionally this is called the velocity potential, and hence inviscid plus irrotational flows are called potential flows, because the velocity is determined by a scalar potential. Now, what is interesting is that the velocity is a vector, it has 3 unknowns, 3 components, Vx, Vy and Vz in Cartesian coordinates. So, in order to solve for the velocity, you have to solve 3 equations, 3 coupled equations, Euler equations, okay, in general. But if the vorticity is 0, then we are saying that instead of solving for 3 velocity components, you can merely solve for 1 function instead of solving for 3 functions, that is, the velocity is a vector function of position variables for steady flows, and the vector function has 3 components, Vx, Vy, Vz, and each of this is a function of the position variables x, y, z. So, instead of solving for 3 unknown functions, you can solve only for 1 unknown function, that is the velocity potential, and once you take the gradient of the potential, you will get back the velocity vector. So, that is a very great simplification that happens when you assume the flow to be irrotational, and as I have told you, irrotational flow is merely a kinematic constraint. But when is that irrotational flow valid? When is the irrotational assumption valid? It makes better sense to use it at higher Reynolds numbers, where you can treat the flow to be effectively inviscid, far away, at least far away from the solid surfaces. So, inviscid and irrotational flows are called potential flows, because the velocity is written as the gradient of a velocity potential, and such potential flows are applicable at high Reynolds numbers in regions away from the solid surface. For regions close to the solid surface, we have to worry about viscous effects, and we will come to that using the boundary layer framework a little later. Okay. So, essentially now what we are simplifying is that we are going to now restrict our attention to potential flows. what I mean by potential flows are the following. Velocity is written as gradient of potential, and since vorticity, that is vorticity is 0, curl of velocity is 0. So, we can write velocity as gradient of potential, but and of course, by using the Euler equation we also found that p by rho plus half v squared plus g z is constant in a potential flow. Okay. Now, these are not all, because our flow is also incompressible. So, you also have in addition the mass conservation equation, that del dot v is 0. Okay. So, if you have v is del phi and substitute that in the mass conservation equation, you have del dot del phi is 0 or simply del squared phi is 0. So, the two constraints on the flow, that the flow is irrotational and the flow is incompressible, means that the velocity potential satisfies a Laplace equation, and the Laplace equation is one of the most well studied equations in any branch of physical science, because it occurs in not just in fluid mechanics, it occurs in heat transfer, mass transfer, it occurs in electrostatics, it occurs in quantum mechanics, and so on and so forth. And so, it has been well studied, and there are lots of methods to solve this linear equation. So, that is the main advantage of working with high Reynolds number potential flows, because there are the velocity is written as gradient of potential, and the potential satisfies Laplace equation through mass conservation condition, that del dot v is 0. Therefore, you have to solve del squared phi is 0. There are many solution techniques, analytical and series solution techniques that are available to solve the Laplace equation. So, that is the simplification that one obtains. Now, there is one thing that we have to understand, that when we went, what are the boundary conditions? To solve this Laplace equation. Okay. When we went from the Navi-Stokes equation to Euler equation, we dropped the viscous term. The viscous terms, the viscous stress term had del squared v. We had del squared, that is second order derivative in space. When we neglected that term, because it is multiplied by 1 over Re in a non-dimensional sense, we have lost the highest order derivative term in the governing equation when we went from the Navi-Stokes to Euler equation. The Euler equation had simply v dot del v term, and del v has only first order gradients in spatial locations. So, if you have just first order differentials in spatial locations, you cannot satisfy both. In principle, if you have potential flow past a solid surface, it has to satisfy both the normal velocity equal to 0 condition and the tangential. If you in principle, if you have flow past a solid surface at any Reynolds numbers, you have to satisfy both the normal velocity condition as well as the tangential velocity condition. Now, the fact that you have lost the highest order derivatives means that we cannot satisfy both the boundary conditions, for the simple reason that that means we would over specify the problem if you want to solve the Euler equation. So, we have to forego one of the two conditions. Now, we will do the least of the we will do away with the least of the evils, that is, we will try to forego the tangential velocity boundary condition rather than the normal velocity condition, because if you say that v dot n is not 0 on a solid surface, that would imply that mass can flow in or out of the solid surface depending on the sign of v dot n. So, that would violate mass conservation, that is a more serious violation. So, compared to that, this is lesser of the two evils, that is, instead of foregoing the normal velocity condition, we will say that we will forego the tangential velocity continuity condition at a solid surface. So, this is a major problem in making the flow or making the assumption that the viscous terms are neglected, in that we are not able to satisfy the no slip condition, and it has major physical implications as we will see a little later. Okay. So, the boundary conditions are that v dot n is 0 on solid surface. Suppose you have solid surface, okay, then there is no, if the solid surface is stationary, then there is no normal component to the velocity. That is the only condition you can satisfy, okay, and cannot satisfy tangential velocity condition. Okay. So, we can get the velocity field for a potential flow, incompressible potential flow, by just solving the Laplace equation for the potential and using the boundary condition that V dot n is 0. But then we are left with one more equation, that is the Bernoulli equation. Here we still have this equation, okay, that P by rho plus half V square plus G Z is constant. Now, what is the use of this extra equation? We have already obtained the velocity profile without using the momentum equation. Remember that this is essentially the momentum balance, the Euler equation rewritten. Now, the answer for that question is that the Bernoulli equation serves to determine the pressure in an inviscid and irrotational flow. So, the procedure to solve potential flow problems is that first use del squared phi equal to 0 to, along with the boundary condition that normal velocity has to be continuous across solids, normal velocity is 0 on a stationary solid. And once you solve for the velocity field, you plug the velocity field back in here and find the unknown pressure through the Bernoulli equation. And pressure is determined only up to a constant, because only gradients of pressures are important in any physical sense. So, pressure can be found only up to a constant in any flow, okay, in incompressible flows. Okay. So, this is the one of the most important simplification that one obtains by looking by making the assumption that the flow is inviscid and irrotational. Now, I am going to make one further assumption. Potential flow assumption is not that the velocity is written as gradient of a potential has no bearing on whether the flow is 2 dimensional or 3 dimensional. It is merely a consequence of the fact that the vorticity is 0 everywhere in the flow. But in order to make further simplifications, at least in this course, we will restrict ourselves to 2 dimensional potential flows, that is, flow is only in the xy plane. The other direction z is so large that there is no variation in the z direction. So, we will assume 2D potential flows from now on. When I say 2D, that means that the velocity vector is written as u times I plus v times j plus w times k. When I say 2D, I mean that there is no w velocity and there is no variation of u and v in the z direction. That is what we mean by 2D, and u is a function of x y and v is a function of x y. They are independent of z. Okay. Now, whenever you have a 2D flow, you can always write u as, use the stream function formulation, partial psi by partial x, v s minus partial psi by partial y, because this automatically satisfies the continuity condition that del dot u is 0. Okay. Now, this is not at all, because we are also saying that omega is 0. In a 2D flow, where the flow is only in the xy plane, the only non-zero velocity is omega z, and since omega is 0, means that omega z is 0 for a 2D flow. For a 2D irrotational flow, we have only one component of non-zero velocity, that is omega z. Okay. So, and since it is irrotational, that has to be 0. So, omega z is nothing but partial v by partial x minus partial u by partial y is 0. Upon substituting the definition of u and v in this expression, you will see that you get partial squared psi by partial x squared plus partial squared psi by partial y squared is 0, or you get del squared psi is 0 in the 2 dimensions x and y. So, the stream function for a 2-dimensional irrotational flow also satisfies the Laplace equation. It is not just the velocity potential that satisfies the Laplace equation. The fact that the only velocity is omega z implies that the stream function also satisfies the Laplace equation in a 2-dimensional potential flow. Okay. So, one can also show that lines of constant psi, that is the streamlines, and constant phi, these are called equipotential, are always orthogonal. Okay. This is something that we can show very easily. So, constant psi means d psi is 0, d psi is partial psi partial x dx plus partial psi partial y dy from basics of multivariable calculus. Partial psi partial x is minus, so we can also rewrite this as saying that dy by dx. So, d psi is 0 means you are along a streamline, because psi is constant means you are along a streamline. So, d psi 0 means you are along a streamline. So, this is the slope of a streamline at constant psi is nothing but dy by dx is nothing but minus partial psi partial x by partial psi partial y. This is nothing but it is v by u, because this u is partial psi partial y, v is minus partial psi partial x. Okay. So, constant phi implies d phi is 0. This will imply that dy by dx, the slope of then equipotential constant phi is minus u by v. So, if you see these two expressions, you have the slope of the slope of stream function, the slope of an equipotential, an equipotential. So, the two slopes m1 m2 multiplied to minus 1, that means that at each point the streamlines and equipotentials are orthogonal to each other. So, to solve for 2D potential flows, all we have to do, so we are restricting ourselves to 2-dimensional potential flows, and the flows will be steady. Okay. So, what do you have to solve for? You have to solve for del squared phi is 0 with the condition that del phi dot n is 0, okay, at solid boundaries. Okay. And we also showed that for 2D potential flows, since the flow is irrotational, there is only one component of vorticity that is non-zero, that is the z component of vorticity. So, we just showed that del squared psi is also 0, where psi is a stream function. And we also showed that lines of constant psi are orthogonal to lines of constant phi. Okay. So, that helps in visualizing the flow in a much easier way, as we will just show in some examples to follow with. Okay. So, now what is the strategy for solving potential flows? We have to solve these two equations. Usually what is done is that we assume a given solution to the, so usually what normally we do in solution of Navi-Stokes is that we have a problem and then we try to solve for the velocity field, okay, by using suitable boundary conditions and by solving the governing equations. Now, here what we are going to do is that we are going to assume some solutions and see to which problem or what physical context does this solution correspond to. Okay. First, so we will treat some elementary potential flows. Where we are going to just assume some solutions of Laplace equations and then see what flows they correspond to. Okay. So, first I will consider uniform flow. I already told you that uniform flow has no vorticity, so it is an irrotational flow. Okay. So, an uniform flow. So, we want to see what an uniform flow is and how it is represented by the velocity potential, what velocity potential corresponds to an uniform flow. Okay. So, consider a uniform flow in the x direction. Okay, there is a constant uniform flow in the x direction. Okay. Now, so the velocity vector has two components u and v. U is capital U while v is 0. Okay. Therefore, you can write u is partial phi by partial x is equal to u, that is also equal to partial psi by partial y. V is partial phi by partial y is 0 is minus partial psi by partial x. Okay. So, we can integrate these two equations partially with respect to x and y. So, this equation will tell us that phi is nothing but, okay, if we integrate this partially with respect to x, it is u x plus constant which could be a function of y, and psi is nothing but u y plus some other constant which could be a function of x. Now, if I do this equation, so phi is nothing but, if I integrate this equation, phi is nothing but a constant, okay, which could be a function of x, okay, and psi is nothing but a constant which could be a function of y. Let's call it c prime d prime to distinguish from these two. So, if you compare these two equations, phi is u x plus constant, it's a function of y, but here phi is a constant only as a function of x. So, this constant c must be 0. Likewise, for psi, it is u y plus a constant of x and it is also a constant of y. So, this constant of x is 0. So, both these equations therefore imply that phi is u x and psi is u y. When phi is u x, when psi is okay, when you phi is u x, you can plot at different values of okay, you can calculate the velocity vector in this simple way that, let's see, okay, at different values of. So, what are equipotentials? Equipotentials are values where of lines where phi is constant. When is phi a constant? For each values of x, phi is a constant. So, equipotentials will be, so for suppose I put a coordinate system like this x y. So, equipotentials will be vertical lines, okay, these are equipotentials. Okay. Now, the streamlines will be obtained by putting different values of y. So, they will be horizontal lines. Okay. The green lines are streamlines, the pink lines are equipotentials. Just by plotting qualitatively sketching lines of phi, constant phi and constant psi, and since it is an uniform flow, it makes sense. The fluid flows from left to right along the x direction. So, the streamlines will be along the horizontal lines along the x direction, and the equipotentials will be vertical lines, because the streamlines and equipotentials are always orthogonal to each other. That is something that we just proved. So, uniform flow has velocity potential of u times x and stream function of u times y. Okay. Now, another problem that we are going to do, another model potential flow is, okay, line source at the origin. Okay. Imagine that you have x, y, z. Imagine that along the z axis you have a very tiny tube, a long tiny tube from which fluid is flowing. Imagine that this fluid, this tube is porous and So, fluid is flowing radially out. Okay. So, there are a lot of holes in this tube. This is just a mental, this is just a model to describe to tell you what a line source could be. In reality, we will just abstract it to a mathematical idiom. Okay. So, you could imagine that you have a long pipe, thin long pipe with lots of pores and then lots of holes, and then imagine that fluid is flowing. So, it has to come out radially, and so the flow is in the xy plane, because there is no flow in the z axis if along the z axis if the length of the tube is very large. So, we are essentially worrying about the flow in the xy plane. In the xy plane, if you look from the top, you look like there is a point from which fluid is flowing radially out. This is called a line source. Okay. It is called a line source. Of course, if you take a cross section, it will look like a point source in the xy plane. Okay. So, it is convenient to use polar coordinates instead of x and y. It is convenient to use r and theta. Okay. Now, if you consider, if you go back to this picture, if you consider an outer cylinder of radius r from the center, and if you consider what is the volumetric flow rate that is crossing this outer cylinder, okay, that is volumetric flow rate. Okay, Q is 2 pi r V r times B, which is the length of the cylinder. Okay. So, this is the volumetric flow rate that flows because the fluid is flowing purely in the radial direction. So, the velocity vector that is coming in is V r. So, 2 pi r is the so you want to multiply that velocity by the area of the cylinder. Area of the cylinder is 2 pi r times B, that is the surface area of the cylinder. So, that will give you what is the volumetric flow rate. Now, we are going to assume that Q is a constant for steady flow. A constant volumetric flow rate keeps coming out from this origin where you had kept this line source of flow. Okay. So, we can write therefore V r is Q by 2 pi B times 1 over r. Now, this is denoted by the letter m, it is a constant. So, V r becomes m over r, where this is called the source strength, the strength of the line source. If m is a positive quantity, then fluid emerges out radially. If m is a negative quantity, fluid comes in, okay, towards origin. Okay, we want to find for this line source of flow mass what is the velocity potential and what is the stream function. Okay. So, V r in cylindrical coordinates is simply partial phi by partial r, and V theta is 1 over r partial phi by partial theta. V r is also equal to, okay, 1 over r partial psi by partial theta. V theta is also equal to minus partial psi by partial r. Okay. For our problem, V r is given by this, but V theta is 0. There is no flow in the theta direction. Flow is purely radial in the cylindrical coordinate system. Okay. So, we can use these two equations to again integrate. Okay. So, V theta is 0, that means partial psi by partial r is 0, okay, because V theta is minus partial psi by partial r, that is also equal to 1 over r partial phi by partial theta. So, if I integrate this with respect to r, I will get psi is some constant which is a function of theta, and I will get phi is equal to, okay. So, m is 2 pi times b. Okay. So, you have 1 over r partial phi by partial theta is 0, which means phi is a constant d, which is a function of r. Okay. So, that means partial phi by partial theta is 0. If you integrate partially with respect to r, this is what you will get. Partially with respect to theta, you will get a constant that is a function only of r. Okay. Now, the other equation tells you that partial phi by partial r is m by r, and this is also equal to or plus 1 over r partial psi by partial theta. This implies if you integrate this equation partially, phi becomes m logarithm of r, okay, plus some constant c prime, which is a function only of theta, and psi becomes, if I integrate this, these two r's will cancel, you will just get m theta plus d prime, which is a function only of r. Okay. So, if I compare these two conditions, psi is a function only of theta from this equation, whereas a function of theta plus r. So, it cannot be a function of r, likewise this constant cannot be a function of theta. So, phi is m logarithm of r and psi is m theta for a uniform source, for a line source. These are the descriptions of velocity potentials and streamlines. So, let us look at lines of constant r. So, lines of constants are circles. Okay. So, the equipotentials are circles, and lines of constant theta are radial lines. Okay. I am going to plot them with pink color. So, these are almost like spokes of a cycle wheel. Okay. These are streamlines, the pink ones are streamlines and the orange ones are equipotentials. And it also agrees with our general result that the stream functions and streamlines and equipotentials are always orthogonal to each other, and that part is of course brought out nicely here. Okay. Now, the next simple example or illustration that I am going to do is a line vortex. Okay. A line vortex is one in which you have, again, if you put an x, y, z coordinate, Cartesian coordinate, okay, at z equal to 0, you can imagine that there is a very long thread of fluid which is rotating at some constant velocity. There is purely circulating motion. Okay. Because of that, there is circulating, all the vorticity in the flow is confined only to the z axis. Okay. So, because of this motion far away, there will be purely circular motion of the fluid. This is called the flow due to a line vortex. Okay. The flow is purely circulation. So, only v theta is there and Vr is 0. This is exactly the opposite of the opposite of the flow which we just discussed, which is a line source problem, where the flow is purely radial and there is no flow in the theta direction. Here we are considering flow only in the theta direction and there is no flow in the radial direction. So, what we want to do is use this idea to find out what the stream functions and velocity potentials are, and we will stop here and we will continue with this topic in the next lecture.